Hello, friend. Some nights when the world goes quiet and the sky opens wide, you might find yourself wondering what lives beyond the light. Out there, past the glow of distant suns, past the edge of what we can see, something waits in the darkness. Not empty, not silent, but folded into itself so deeply that even light cannot escape. Tonight we're going to drift toward the edge together, the place where stars go to dream, where gravity bends so far it breaks, where the universe keeps its most beautiful, most terrifying secret: black holes. But not the black holes you might imagine, not the cosmic vacuum cleaners of science fiction, not the destroyers swallowing galaxies whole. No, tonight we're going somewhere stranger. We're going to explore what happens when the largest objects in the universe meet the smallest rules of reality. When Einstein's equations shake hands with quantum mechanics in the dark. We're going to whisper about the quantum nature of black holes. Before we begin our quiet journey into the impossible, if you find comfort in these slow drifts through science, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell. Not for noise, but so the next quiet night can find you again. Thank you for being here. Now, let's drift. Imagine standing at the edge of everything you know. Behind you, the familiar universe, stars burning in their ancient rhythms, planets spinning their patient circles. But ahead, just one step forward, the rules change completely. Space doesn't just curve there, it folds. Time doesn't just slow, it stops. Light doesn't just bend, it surrenders. This is the event horizon, the threshold, the point of no return. And here's what makes it strange, what makes it worth staying awake just a little longer to understand. A black hole isn't really a hole at all. It's the opposite. It's the most concentrated mass in the universe, squeezed into a space so small that mathematics itself starts to whisper uncertainties. Picture this. Take our sun, massive and bright, burning with the energy of 4 million tons of hydrogen every second. Now, imagine crushing it, compressing all that light, all that heat, all that nuclear fire into a sphere just 6 kilometers across, small enough to fit inside a city. The gravity there wouldn't just be strong, it would be absolute. But our sun will never become a black hole. It's not heavy enough. It will grow old, expand into a red giant swallow, the inner planets perhaps then fade into a white dwarf, a cosmic ember, cooling slowly across billions of years. Black holes need violence to be born. They need stars that live fast and die catastrophically. Stars 20, 30, 50 times more massive than our sun. Stars that burn so bright, they exhaust their fuel in just a few million years, not billions. These giants, when they reach the end, when the fusion in their cores finally stops, they collapse. Not slowly, not gently. In less than a second, the core implodes. The outer layers rebound in a supernova, an explosion so bright it can outshine an entire galaxy for weeks. But the core, the heart of the star, it keeps falling. Inward, always inward. Past the point where atoms can resist. Past the point where even neutrons packed as tight as matter can be finally give up. And then something remarkable happens. Something that still makes physicists pause and question. The collapse doesn't stop at any surface. It continues past any boundary we can imagine, folding space around it, creating what we call a singularity. A point of infinite density where the laws of physics as we understand them simply dissolve into mystery. This was predicted mathematically before we ever observed one. In 1916, just months after Einstein published his theory of general relativity, a German physicist named Karl Schwarzschild was serving in the German army during World War I. He was calculating artillery trajectories by day. But at night in the trenches by candlelight, he was solving Einstein's equations. And he found something Einstein himself didn't expect. He found that if you compressed enough mass into a small enough space, you would create a region from which nothing could escape, not even light. Einstein didn't believe it at first. He thought nature would find a way to prevent such extremes. But the mathematics didn't care what anyone believed. Schwarzschild's solution described a radius now called the Schwarzschild radius, a boundary around any mass. For the Earth, that radius is about 9 millimeters. For the Sun, about 3 kilometers. If you could somehow compress all the mass of these objects inside their Schwarzschild radius, they would become black holes. But nature, as far as we know, only does this to the most massive stars. And when it doesn't create chaos. It creates something almost elegant. A black hole doesn't roam around consuming everything in sight. It orbits. It pulls on nearby objects with gravity just like any star would. If our sun suddenly became a black hole right now, the Earth wouldn't fall in. It would keep orbiting just in colder darkness. The danger isn't in getting close, it's in getting too close. In crossing that invisible line, the event horizon where escape becomes impossible. Scientists have found black holes of different sizes scattered across the cosmos. Stellar black holes born from dying stars typically range from 3 to 20 times the mass of our sun. Intermediate black holes, still mysterious and rare, might be hundreds or thousands of solar masses. And then there are the monsters, the supermassive black holes that lurk at the centers of most galaxies, including our own. Our galaxy, the Milky Way, has one, Sagittarius A star, 4 million times the mass of the Sun, sitting quietly at the galactic center, 26,000 light-years away. For years, astronomers watched stars orbiting something invisible there, moving at thousands of kilometers per second. Their paths bent by gravity so strong, it could only mean one thing. In 2022, we finally saw it. Not the black hole itself, you can't see darkness, but the glowing ring of superheated gas swirling around it, the accretion disk matter spiraling inward at nearly the speed of light, heating to billions of degrees in its final moments before crossing the horizon. That image, blurry and orange and historic, showed us the shadow, the silhouette of a black hole against the light it was bending around itself. Einstein's prediction visualized. 100 years of mathematics made real. But here's where the story gets stranger. Where the universe shows us it's not content with just one set of rules. Because black holes, as extreme as they are, live in the realm of general relativity. The physics of the very large, curved space-time, smooth, continuous, deterministic. A fabric that can be bent but never torn. Quantum mechanics, on the other hand, is the physics of the very small. Atoms, particles, probabilities and uncertainties. A reality that flickers and jumps and refuses to be pinned down. Where things can be in two places at once. Where particles pop in and out of existence. Where the act of observing changes what you're observing. For most of the universe, these two languages never have to speak to each other. General relativity handles stars and galaxies. Quantum mechanics handles electrons and photons. They work, they predict, they rarely overlap. But at the event horizon of a black hole, they collide. The very large meets the very small. Infinite gravity meets quantum uncertainty. And neither theory knows what to do. This is where the quantum nature of black holes begins. Not in what we know, but in what we cannot reconcile. In the beautiful, maddening fact that our two best theories of reality, both tested and proven again and again, contradict each other when pushed to this extreme. Stephen Hawking saw this first. In the 1970s, trying to understand what happens near a black hole's event horizon, he combined quantum field theory with general relativity. Just a little, just enough to ask a simple question. What happens to the quantum vacuum near a black hole? Empty space, according to quantum mechanics, isn't truly empty. It seethes with virtual particles. Pairs of matter and antimatter that pop into existence exist for a fraction of a second, then annihilate back into nothing. Normally, we never notice them. They borrow energy from the vacuum, pay it back immediately, and vanish. But near an event horizon, something different can happen. If a particle-antiparticle pair appears right at the boundary, one particle might fall into the black hole while the other escapes into space. To an outside observer, it would look like the black hole is emitting particles, like it's glowing ever so faintly with thermal radiation. Hawking proved this mathematically. He showed that black holes aren't completely black. They radiate, they have a temperature, and over unimaginably long time scales, trillions upon trillions of years, they evaporate. This was revolutionary, disturbing, beautiful. It meant black holes could die. It meant they connected thermodynamics, quantum mechanics, and gravity in ways no one had imagined. But it also created the biggest paradox in modern physics, the information paradox. If black holes evaporate, where does the information go? Everything that falls in every particle, every pattern, every detail about the star that collapsed, the astronaut who crossed the horizon, the book that was thrown in all of it, encoded in quantum states. Does it vanish? Quantum mechanics says information can never be destroyed. General relativity says it disappears behind the horizon forever. Both cannot be right. Yet both have been tested, proven, trusted. For nearly 50 years, physicists have wrestled with this, debated, proposed wild solutions, holographic principles, firewalls, wormholes connecting entangled particles, each idea stranger than the last, each trying to reconcile the irreconcilable. And we still don't know the answer, not completely, not yet. But here's what makes this beautiful, the not knowing. The fact that the universe has given us a puzzle so deep, so fundamental, that solving it might rewrite everything we understand about reality itself, about space, about time, about information and entropy and existence. Black holes are not just objects in space, they are questions. Cosmic laboratories where nature tests its own limits, where the very big and the very small finally have to meet, have to speak, have to find a common language. Maybe that language is strings vibrating in 11 dimensions. Maybe it's loops of space-time woven at the Planck scale. Maybe it's something we haven't imagined yet, waiting in the mathematics, waiting for someone to ask the right question in the right way. Do you ever wonder if the answers are already out there, written in the way black holes spin in the ripples they make, when they collide in the faint radiation they emit across eons, waiting for us to learn how to listen? The journey to understanding doesn't end at the edge of the event horizon. It begins there. Because to truly know what a black hole is, we have to understand what happened in the moments of its birth, in the violence and beauty of a star's final collapse. And that's where we'll drift next, into the heart of darkness, being born into the strange and certain process that turns light into shadow, matter into mystery, the story of how stars fold into infinity. A star doesn't know it's dying, not at first. For millions of years, it burns bright, fusing hydrogen into helium in its core, balancing perfectly between the crush of its own gravity and the outward pressure of nuclear fire. It's a dance, elegant, stable. A fusion reactor suspended in space, held together by forces so precise they seem almost intentional. But nothing burns forever. When a massive star, one born with 20 or 30 or 50 times the mass of our sun, begins to run low on hydrogen, something shifts. The core contracts, the temperature rises, and the star doesn't die. Not yet. It adapts. It starts fusing helium into carbon, then carbon into neon, neon into oxygen, oxygen into silicon. Each stage burns faster than the last. Hydrogen fusion can last 10 million years. Helium, maybe 1 million. Carbon, just a few centuries. Silicon fusion, the final stage before collapse, lasts about 1 day. 1 day. Imagine that. A star that has burned steadily for millions of years, suddenly racing through its fuel in hours, like a candle flickering in its last moments, bright and desperate and beautiful. And then the core becomes iron, and everything stops. Iron is different. Iron doesn't release energy when it fuses, it absorbs it. So when the core fills with iron, the fusion stops. The pressure vanishes. And for the first time in the star's life, there's nothing pushing back against gravity. What happens next is almost too fast to believe. The core, now supported by nothing but the quantum pressure of electrons refusing to occupy the same space, reaches a limit. The Chandrasekhar limit, named after the Indian astrophysicist Subrahmanyan Chandrasekhar, who calculated it in 1930 while traveling by ship from India to England. He was 19 years old. He showed that if a stellar core exceeds about 1.4 times the mass of the Sun, electron pressure can no longer hold it up. The core collapses, and it doesn't collapse slowly, doesn't crumble over days or years. It implodes in less than a second. Less than a second for an object the size of Earth to crush itself into a sphere 15 kilometers across. The atoms shatter. Electrons merge with protons to form neutrons. The density becomes unimaginable. A sugar cube of neutron star material would weigh 1 billion tons on Earth. But the collapse releases energy, enormous energy. The outer layers of the star, still falling inward, hit this impossibly dense core and rebound. They explode outward in a supernova, a blast so bright it can be seen across billions of light years, shining with the light of 100 billion suns for weeks. In 1054 AD, Chinese astronomers recorded a guest star in the constellation Taurus. It appeared suddenly bright enough to see in daylight, for 23 days, visible at night for nearly 2 years. They didn't know they were watching a supernova. The remnant of that explosion, the Crab Nebula, is still expanding today, a glowing cloud of gas and dust, with a rapidly spinning neutron star at its heart, pulsing 30 times per second like a cosmic lighthouse. But not all cores stop at neutron stars. If the core is massive enough, above about 3 solar masses, even neutron pressure cannot hold it up. The collapse continues. Past the neutron star stage, past any known state of matter, into something for which we have no complete theory: a singularity. Scientists describe it as a point of infinite density, but infinity is a word that makes physicists uncomfortable. It usually means the equations are breaking down, pointing toward physics we don't yet understand. What we do know is this: the collapsing core doesn't stop at a surface. It keeps falling, and as it does, it warps space-time around itself so severely that a boundary forms. The event horizon. From the outside, it looks like the collapse freezes at this boundary. Time dilation becomes so extreme that light from the collapsing matter redshifts, infinitely fading to black before it ever appears to cross. An outside observer never sees the final moment. The surface seems to hang there, frozen at the edge of the event horizon, dimming into darkness over time. But from the perspective of the matter itself, the infalling perspective, there's no pause. It crosses the horizon in finite time and continues inward. And this is one of the strangest features of black holes. They exist in 2 realities at once. Outside, time slows to a stop at the horizon. Inside, everything happens normally, rushing toward the center. There are different kinds of black holes born from this violence. The smallest stellar black holes, formed from stars just massive enough to collapse, might be only 3 or 4 times the sun's mass, with event horizons 20 to 30 kilometers across. Larger ones, from more massive progenitors, can reach 20, 50, even 100 solar masses. Then there are the mysteries. Intermediate mass black holes, somewhere between stellar and supermassive. We've detected hints of them, gravitational wave signals suggesting black holes hundreds of times the sun's mass. But we don't fully understand how they form, perhaps from repeated mergers, perhaps from the direct collapse of massive gas clouds in the early universe, perhaps from processes we haven't imagined yet. And at the centers of galaxies, the giants, supermassive black holes millions or billions of times the mass of the sun. Our Milky Way harbors Sagittarius, a star 4 million solar masses packed into a region smaller than Mercury's orbit. The galaxy M87, imaged by the Event Horizon Telescope in 2019, hosts a monster 6.5 billion solar masses. Its event horizon could swallow our entire solar system. How these supermassive black holes formed is still debated. They were already enormous when the universe was young, less than 1 billion years old, too massive to have grown from stellar black holes alone in the time available. Some scientists suggest they formed from the direct collapse of huge primordial gas clouds. Others think they grew through rapid accretion and mergers in the dense early universe. The truth might be a combination different formation. Pathways creating the cosmic ecology of black holes we observe today. But here's a common mistake people make when they first learn about black holes. They imagine them as cosmic vacuum cleaners roaming through space, sucking up everything nearby. Hollywood loves this image. Spaceships spiraling helplessly inward, planets torn apart, galaxies consumed. That's not how gravity works. A black hole's gravity at a distance is no different from the gravity of the star that formed it. If our sun suddenly became a black hole, the Earth wouldn't spiral inward. It would keep orbiting at the same distance in the same orbit, just in permanent night. The gravity wouldn't change, only the source would compress. The danger comes from proximity, from crossing into the region where tidal forces, the difference in gravitational pull between your head and your feet, become extreme. For a supermassive black hole, you could cross the event horizon and not immediately notice anything wrong. The tidal forces at the horizon of Sagittarius A star are relatively gentle. You'd have time perhaps hours before reaching the singularity. But for a stellar mass black hole, the tides are vicious. Long before you reach the event horizon, the difference in gravity between your feet closer to the black hole and your head farther away would stretch you into a thin stream of atoms. Astrophysicists have a term for this: spaghettification. It sounds almost playful until you think about what it means. Your body stretched like taffy, every molecule pulled apart by forces millions of times stronger than anything on Earth. In 1930, Chandrasekhar's calculations on that ship voyage from India weren't immediately celebrated. When he presented his findings at the Royal Astronomical Society in 1935, Arthur Eddington, one of the most respected astronomers of the time, publicly dismissed them. Eddington couldn't accept that stars could collapse beyond the neutron star stage. He thought there must be some mechanism, some law of nature that would prevent such absurdity. But nature doesn't care what we find absurd. The mathematics was correct. And within a few decades, observations began confirming what the equations predicted. Neutron stars were discovered through their radio pulses in 1967. Black hole candidates were identified through X-ray emissions from superheated accretion disks in the 1970s. The merger of two black holes was detected through gravitational waves in 2015. Each discovery refined our understanding, but also deepened the mystery. Because while we can describe what happens during a collapse, while we can calculate the event horizon and predict the space-time curvature, we still can't fully explain what exists at the very center. The singularity is where our physics breaks, where general relativity so precise and predictive everywhere else gives us infinities, infinite density, infinite curvature, zero volume containing finite mass. These are signs that the theory is incomplete, that we're missing something fundamental about how gravity behaves at the smallest scales. And this is where quantum mechanics must enter, where the smooth, deterministic curves of space-time meet the discrete, probabilistic quantum world, where we need a theory of quantum gravity, a way to describe what happens when you compress matter beyond the Planck scale, the smallest meaningful length in physics, about 10 to the power of minus 35 meters. String theory proposes that at this scale, space-time itself is woven from vibrating strings of energy. Loop quantum gravity suggests it's made of discrete loops, a fabric with texture not smooth at all. Both are attempts to avoid the singularity, to replace the infinite point with something finite and quantum. Maybe the singularity doesn't exist. Maybe at the very center of a black hole, quantum effects prevent the collapse from reaching infinite density, creating instead a tiny, incredibly dense core, a Planck star, bouncing and radiating quantum information in ways we can barely imagine. Or maybe the singularity is real, and our discomfort with infinity is just our limited perspective, our inability to conceive of what space-time becomes when pushed to its ultimate extreme. Have you ever wondered what it would look like falling into a black hole? Not from the outside where you'd see someone redshift and freeze at the horizon, but from the inside, from the perspective of the fall itself. The stars above would distort, compress into a shrinking circle of light as space-time curves around you. The black hole's gravity would lens the light from behind, bending it forward, creating a kaleidoscope of warped starlight. Time would feel normal to you, but the universe outside would accelerate. You'd watch the cosmos, age stars, dying, galaxies colliding, all compressed into moments. And then darkness. Not the darkness of closed eyes, but absolute darkness, the absence of all light. Because you've crossed the horizon, and no light from outside can catch up to you anymore. These are the graves where stars go, when they can no longer fight gravity. These are the monuments to matter's final surrender, the places where the universe's most fundamental forces push reality past its breaking point. But the story doesn't end with birth, with the violent creation of the event horizon. Because once formed, a black hole becomes something stranger than just a collapsed star. It becomes a boundary, a membrane between what can be known and what is forever hidden. And at that boundary, at the very edge where space folds into itself, physics reveals one of its most profound secrets. A threshold that once crossed erases every path back to the light. There are places in the universe you can visit and leave, planets, stars, even the surface of a neutron star if you could somehow survive the gravity. But there is one boundary invisible and absolute that offers no return ticket. Cross it, and every direction you try to move leads deeper inward. Every path forward becomes a path toward the center. Light itself cannot climb back out. This is the event horizon, not a physical surface, not a wall you could touch, but a point of no return woven into the fabric of space-time itself. The event horizon exists at a precise distance from the center of a black hole, a radius calculated by Carl Schwarzschild in those trenches during World War I. The formula is elegant, simple. The Schwarzschild radius equals 2 times the gravitational constant, times the mass divided by the speed of light squared. Compress any mass inside this radius, and you create an event horizon, a one-way membrane in reality. For Earth, that radius is 9 millimeters, a marble. For the Sun, about 3 kilometers. For Sagittarius A star, the supermassive black hole at the center of our galaxy, the event horizon stretches about 12 million kilometers across, 16 times the distance from the Earth to the Sun. A sphere so vast it could contain the orbit of Mercury, with room to spare. But size doesn't change the fundamental nature of what it is. Whether it's the size of a marble or the size of a solar system, the event horizon marks the same absolute boundary, the point where the escape velocity equals the speed of light. Escape velocity is the speed you need to break free from a gravitational field. On Earth, it's about 11 kilometers per second. Launch a rocket faster than that, and it will escape into space. Launch it slower, and gravity pulls it back down. The moon's escape velocity is lower, about 2.4 kilometers per second. Jupiter's is higher, almost 60 kilometers per second. As you approach a black hole, the escape velocity increases, 10 kilometers per second, 1,000, 10,000, 100,000. And at the event horizon, it reaches exactly 299,792 kilometers per second, the speed of light, the cosmic speed limit. Nothing in the universe can move faster, so nothing, not even light, can escape. This is why black holes appear black, not because they absorb light like a dark surface, but because any light that crosses the event horizon can never return to tell us it's there. The photons fall inward, following the only paths space-time allows, and those paths all lead to the singularity. But here's something subtle, something easy to misunderstand. The event horizon isn't a place where gravity suddenly becomes infinite. Gravity at the event horizon of a supermassive black hole can actually be quite gentle. Sagittarius A**'s event horizon has tidal forces you could survive, at least briefly. You could, in theory, cross it without being immediately torn apart. The danger isn't the strength of gravity at the horizon. It's the geometry of space-time itself. Inside the event horizon, the roles of space and time switch in a way that defies everyday intuition. Moving toward the singularity becomes as inevitable as moving forward in time. You can no more avoid reaching the center than you can avoid reaching the next second. Outside the event horizon, you can choose where to move in space. Left, right, forward, backward, up, down. Time is fixed, flowing in one direction, but space is yours to navigate. Inside the event horizon, this reverses. The direction toward the singularity becomes temporal, not spatial. It becomes your future, unavoidable and certain. Every moment that passes brings you closer, not because you're moving through space, but because you're moving through time. Physicist Kip Thorne described it this way. Imagine you're floating just outside the event horizon, holding position with rockets. You look at your watch. 1 second passes, 2 seconds, 3. Time flows normally for you, but your rockets are fighting an increasingly steep gravitational gradient, burning fuel to stay in place. Now, you cross the horizon. You turn off your rockets thinking you'll just drift for a moment before turning back. But there is no turning back. The singularity is no longer a place in space you can avoid. It's a moment in your future approaching as inevitably as tomorrow. You could fire your rockets at full power in any direction, and all you do is change how long it takes to reach the center, not whether you reach it. This is the horror and the beauty of the event horizon. It's a boundary where the future becomes unavoidable, where all paths converge on a single destination. From the outside, though, the event horizon presents a different mystery: time dilation. As you watch someone fall toward a black hole, you see them slow down, not because they're moving slower, but because time itself is stretching near the horizon. Their clock ticks slower compared to yours. Their movements become sluggish, then glacial, then frozen. They never appear to cross. Instead, they freeze at the horizon, their image red shifting, dimming, fading into infrared, then radio waves, then nothing. The light from their final moments takes longer and longer to reach you, stretched by the infinite time dilation at the boundary. But from their perspective, nothing special happens at the event horizon. They cross it in the finite time. Their clock ticks normally. They see the stars above them compress into a bright ring, the universe outside accelerating due to time dilation. But they feel no barrier, no surface, no moment of crossing. Only later, as tidal forces grow, as the singularity approaches, does the violence begin. This duality, this difference in perspective, is one of the strangest features of black holes. Two observers, one falling, one watching, experience completely different realities. And both are correct, both are true. Relativity doesn't choose a preferred viewpoint, it honors both. In 1939, Robert Oppenheimer and his student Hartland Snyder published a paper describing the collapse of a massive star. They showed mathematically that from the outside perspective, the collapse appears to freeze just outside the Schwarzschild radius, the surface dimming and red shifting, but never quite finishing. Yet from the perspective of the collapsing matter, the process completes in finite time, forming an event horizon and continuing inward. This paper was largely ignored for decades. The idea seemed too strange, too removed from physical reality. World War II and the development of nuclear weapons diverted attention. Black holes remained mathematical curiosities, solutions to Einstein's equations that most physicists assumed nature would never actually produce. It wasn't until the 1960s when astronomers began discovering quasars, incredibly bright objects at the centers of distant galaxies, that black holes became serious candidates for real astrophysical objects. The only way to explain the enormous energy output of quasars brighter than 1,000,000,000,000 suns from a region smaller than our solar system was accretion onto supermassive black holes. And in 1971, the first strong black hole candidate was identified. Cygnus X1, an X-ray source in the constellation, Cygnus appeared to be a massive invisible object orbiting a blue supergiant star, pulling matter from it in a glowing accretion disk. The X-rays came from the superheated gas spiraling inward, reaching millions of degrees just before crossing the event horizon. Stephen Hawking famously bet against Cygnus X1 being a black hole, a bet he described as insurance. If black holes didn't exist, at least he'd win the bet. In 1990, he conceded, acknowledging the evidence had become overwhelming. The invisible companion was too massive to be a neutron star, too compact to be anything but a black hole. Today we've identified thousands of black hole candidates. We've imaged the event horizons of 2 supermassive black holes using radio telescope arrays spanning the Earth. We've detected the gravitational waves from dozens of black hole mergers events so violent they shake space-time itself, sending ripples across the universe at the speed of light. But despite all this observational success, the event horizon itself remains deeply mysterious at the quantum level. Because while general relativity describes it perfectly as a smooth, classical boundary, quantum mechanics suggests something stranger might be happening there. Information in quantum mechanics is never destroyed. It can be scrambled, hidden, transformed, but never erased. This is a fundamental principle tested and verified in countless experiments. Yet, when something falls into a black hole crossing the event horizon, it seems to vanish from the universe. All the information about its quantum state, its history, its structure, appears to be lost. This contradiction, the information paradox, has haunted physics for 50 years. And it all centers on the event horizon, on what happens at that boundary, on whether information truly disappears or is somehow preserved in ways we don't yet understand. Some solutions propose that the event horizon is actually a firewall, a region of incredibly high energy that destroys anything trying to cross, incinerating it instantly and releasing its information as radiation. This would mean there's no smooth crossing, no gentle fall, just instant annihilation. Other solutions suggest the information is never truly lost, but encoded on the event horizon itself, holographically imprinted on the surface in a way that allows it to be recovered through Hawking radiation over eons. This is called the holographic principle, and it implies that everything inside a black hole can be described by information on its 2-dimensional surface. Both ideas are radical. Both challenge our understanding of what the event horizon actually is. Is it a benign mathematical surface, a coordinate singularity where nothing special happens locally? Or is it a physical boundary with quantum properties we're only beginning to glimpse? We don't know yet. And this not knowing is part of what makes black holes so compelling. They're not just objects in space. They're experiments that nature has set up for us, testing grounds where our theories confront their limits. Do you think information can truly vanish, or must the universe somehow always keep track? The event horizon is where this question becomes unavoidable, where the classical description breaks down and quantum mechanics demands a voice. And understanding what happens there truly happens at the deepest level requires us to explore a discovery that shocked even Einstein, a revelation that black holes are not entirely black, that they glow with a faint ghostly radiation, carrying secrets about the quantum nature of space-time itself. In 1974, a young physicist at Cambridge University made a calculation that would change everything we thought we knew about black holes. His name was Stephen Hawking. He was 32 years old, already confined to a wheelchair by motor neuron disease, already celebrated for his work on singularities and the origins of the universe. But what he discovered that year, working quietly through the mathematics of quantum fields near event horizons, shocked even him. Black holes are not eternal. They glow. They evaporate. And given enough time, trillions upon trillions of years, they disappear completely. The universe, it seemed, had found a way to erase even the darkest objects in existence. Not through violence, not through collision, but through the gentle, patient whisper of quantum mechanics. Empty space, according to quantum field theory, is never truly empty. It seethes with activity, with virtual particles constantly popping into existence in matter-antimatter pairs. An electron and a positron, a quark and an antiquark, they appear borrowed from the quantum vacuum, exist for an infinitesimal fraction of a second, then annihilate back into nothing. This isn't speculation, it's measurable. The Casimir effect, first predicted in 1948 and experimentally confirmed in 1997, shows that two metal plates placed close together in a vacuum experience a tiny attractive force. The space between them allows fewer virtual particle pairs than the space outside, creating a pressure difference. Quantum fluctuations have real physical consequences. Hawking asked a simple question: what happens to these virtual particles near an event horizon? Normally, particle pairs appear and disappear so quickly that energy conservation is never violated, not even momentarily. The uncertainty principle allows them to borrow energy from the vacuum as long as they pay it back fast enough. But near an event horizon, something remarkable can occur. If a particle-antimatter pair appears right at the boundary, one particle might fall into the black hole while the other escapes into space. To an outside observer, it looks like the black hole is emitting a particle, like it's radiating. And if the black hole is losing particles, it's losing mass, slowly, imperceptibly, but measurably, at least in principle. Hawking worked through the mathematics, carefully combining quantum field theory with the curved space-time of general relativity. The calculation was complex, delicate, requiring him to track how quantum fields behave in the extreme gravitational gradient near an event horizon. What emerged was a formula of beautiful simplicity. The temperature of a black hole is inversely proportional to its mass. Smaller black holes are hotter. Larger black holes are colder. A black hole with the mass of the Sun would have a temperature of about 60 nanokelvins. 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that fills the universe at 2.7 Kelvin. This means stellar mass black holes don't actually evaporate in our current universe. They absorb more radiation from the cosmic background than they emit through Hawking radiation. They grow very slowly rather than shrink, but the universe is cooling. As it expands the cosmic microwave background, redshifts its temperature dropping. In about 10 to the power of 19 years, about a billion times the current age of the universe, the background radiation will cool below the Hawking temperature of stellar mass black holes. And then finally, they'll begin to evaporate. The process is slow beyond comprehension. A black hole with the mass of the Sun would take 10 to the power of 67 years to evaporate completely. That's a 1 followed by 67 zeros. For comparison, the universe is only about 10 to the power of 10 years old. A billion times, a billion times, a billion times, a billion times longer than the universe has existed. But smaller black holes evaporate faster, much faster. A black hole with the mass of a mountain about 1 billion tons would have a Hawking temperature of about 100 billion Kelvin, hot enough to emit gamma rays, and it would evaporate completely in about 10 billion years, roughly the current age of the universe. Even smaller black holes, if they exist, would be incredibly hot. A black hole with the mass of an aircraft carrier would shine with the power of a large nuclear reactor and evaporate in seconds. A black hole the mass of a person would explode with the energy of a hydrogen bomb almost instantly. We've never detected Hawking radiation directly. The effect is too weak for any black hole we've observed. But the theoretical prediction is solid, built on principles we trust. Quantum field theory in curved space-time, the equivalence principle, the conservation of energy. If these foundations are correct, and they've been tested extensively in other contexts, then Hawking radiation must exist. What makes this discovery so profound isn't just that black holes evaporate. It's what it reveals about the nature of information entropy and the quantum structure of space-time itself. Because Hawking radiation, as originally calculated, appears to be thermal, random. It carries no information about what fell into the black hole. Imagine you throw a book into a black hole. That book contains information. The arrangement of words, the sequence of letters, the quantum states of every atom. In classical general relativity, that information crosses the event horizon and is gone hidden behind the boundary, inaccessible, but still existing somewhere inside. But if the black hole evaporates, if it slowly radiates away all its mass as thermal Hawking radiation, where does the information go? Thermal radiation is random, like the heat from a fire. It doesn't encode specific information about what burned. It's just temperature entropy disorder. This is the information paradox. Quantum mechanics says information can never be destroyed. It can be scrambled, hidden in correlations, spread across entangled states, but never erased. Yet Hawking radiation, being thermal, appears to destroy information. And when the black hole finally evaporates completely, that information seems to vanish from the universe entirely. For decades, this paradox divided physicists. Hawking himself initially believed information was lost, that black holes were the one exception to the rules of quantum mechanics. Others, including Leonard Susskind and Gerard 't Hooft, argued fiercely that information must be preserved somehow, that we were missing something fundamental about how black holes work at the quantum level. The debate became famous, heated, personal at times. Hawking and Susskind would argue at conferences, each defending their position with passion and precision. It wasn't just an academic disagreement. It was a fight over the fundamental laws of physics, over whether the universe plays by consistent rules or allows exceptions. In 2004, Hawking conceded. He announced at a conference in Dublin that he'd been wrong, that information is not lost in black holes. The Hawking radiation, he now believed, must carry information out, encoded in subtle correlations between the particles in ways too complex for the original calculation to capture. But conceding that information survives doesn't solve the paradox. It just shifts the question. How does the information get out? How can thermal radiation, which looks random, actually encode specific quantum states? The mathematics of this process, the precise mechanism, remains one of the deepest unsolved problems in theoretical physics. One clue comes from the temperature itself. Hawking's formula reveals something strange. The temperature of a black hole depends only on its mass, not on what fell into it. A black hole made from hydrogen has the same temperature as one made from iron or starlight or grand pianos, as long as the mass is the same. This suggests that black holes have entropy. They have a measure of disorder of hidden information, and that entropy is proportional to the area of the event horizon, not the volume. A black hole with 4 times the mass has 4 times the area and 4 times the entropy. This area law is bizarre. Normally, entropy scales with volume. A box twice as large can hold twice as many particles, roughly twice as much disorder. But black holes don't follow this rule. Their entropy depends on their surface area, as if all the information about what's inside is somehow encoded on the 2-dimensional event horizon. Jacob Bekenstein proposed this in 1972, even before Hawking discovered the radiation. He argued that black holes must have entropy proportional to their area. Otherwise, you could violate the second law of thermodynamics by throwing hot objects into black holes. Hawking's calculation confirmed this, providing a precise value for the entropy. The Bekenstein-Hawking entropy of a black hole is enormous. A black hole with the mass of the Sun has an entropy about 10 to the power of 54 times larger than the Sun itself. That's the amount of information you could theoretically encode on the event horizon, measured in fundamental units called Planck areas, the smallest meaningful patches of space. This connection between area and entropy hints at something profound. It suggests that space-time itself might be holographic, that the information content of any region can be described by data on its boundary. The universe in this view might be like a hologram, where a two-dimensional surface contains all the information needed to reconstruct a three-dimensional volume. But Hawking radiation creates another puzzle. As a black hole evaporates, it gets smaller. Its event horizon shrinks. Its temperature increases. The radiation becomes more intense. And in the final moments when the black hole has shrunk to near Planck mass, about 22 micrograms, it should explode in a burst of high-energy particles. What happens in that final moment? Does the singularity simply vanish? Does it leave behind a remnant, a tiny quantum object that carries all the information? Or does the explosion somehow release the information encoded on the event horizon, unscrambling it in ways we can't yet calculate? We don't know. The final stages of black hole evaporation require a complete theory of quantum gravity, a framework that doesn't yet exist. String theory loop quantum gravity and other approaches make different predictions, but none can be tested with current technology. There's something almost poetic about Hawking radiation, about the idea that black holes, the darkest objects in the universe, slowly return their stolen light to the cosmos. That nothing is permanent, not even the gravitational prisons that trap starlight itself. That quantum mechanics patient and persistent finds a way to reclaim what gravity tried to hide forever. Have you ever thought about how long infinity feels? How many years it would take to watch a black hole fade one photon at a time across time scales that dwarf the age of stars? The universe is patient. It doesn't rush. And in that patience in the slow quantum whisper of Hawking radiation lies a clue to something deeper. Because the information paradox isn't just about black holes. It's about whether the universe has memory, whether the past leaves traces that can never be erased, whether reality itself is fundamentally reversible, or if some knowledge can be lost forever. And resolving this question will take us into even stranger territory, into the quantum entanglement between particles and the geometric connections that might link them across space and time. Imagine you have a book, an old book filled with poems, equations, memories written in careful handwriting. Every word matters. Every arrangement of letters carries meaning. Now imagine you burn that book. The pages curl, black and turn to ash. The smoke rises and disperses into the atmosphere. Is the information gone? At first it seems obvious. Of course it is. The words are unreadable, the pages destroyed. But physics says something different. Physics says that if you could track every atom of smoke, every photon of light from the flames, every vibration in the air, you could in principle reconstruct what the book said. The information isn't destroyed, it's scrambled, hidden in correlations between particles so complex that recovering it is practically impossible, but theoretically allowed. This is a fundamental principle of quantum mechanics. Information is never lost. The universe remembers. Every quantum state, every particle interaction, every moment of history leaves traces that cannot be erased. But black holes seem to break this rule. And that contradiction, that impossible tension between quantum mechanics and general relativity is called the information paradox. It's been called the most important problem in theoretical physics, the puzzle that might finally force us to understand what space-time really is at its deepest level. The paradox begins with what we've already explored: Hawking radiation. Black holes evaporate by emitting thermal radiation, random particles with no apparent connection to what fell in. If you throw that book into a black hole, then wait for the black hole to evaporate completely. The radiation coming out appears to be pure thermal noise, random, uncorrelated, carrying no information about the book or anything else that fell in. This violates quantum mechanics completely. If information is truly lost, then quantum evolution isn't reversible. The past cannot be reconstructed from the present. Determinism breaks down. and experiments in quantum systems from particle collisions to quantum computers have never shown information loss. Not once. The rules are consistent. Until black holes. Stephen Hawking argued for years that black holes were the exception, that quantum mechanics simply didn't apply to gravitational collapse. That information genuinely disappeared when it crossed the event horizon, lost to the singularity, erased from reality. But this created its own problems. If information can be destroyed, then entropy isn't conserved. The second law of thermodynamics, which says disorder never decreases in a closed system, could be violated. You could reduce the universe's total entropy by throwing high-entropy objects into black holes, making them vanish. Leonard Susskind, a physicist at Stanford, found this intolerable. He spent years arguing with Hawking, insisting that quantum mechanics must be preserved, that information must somehow escape black holes, even if we didn't yet understand how. The debate became legendary conferences where two brilliant minds clashed over the foundations of reality. In 1997, the argument intensified into what's now called the Black Hole War. Susskind and T. Hooft proposed a radical solution, the holographic principle. The idea that all the information about the interior of a black hole is encoded on its event horizon on the two-dimensional surface like a hologram, encoding a three-dimensional image. This seems impossible at first. How can 3 dimensions of information fit onto 2 dimensions? How can the complexity of everything inside a black hole, the particles, the fields, the quantum states, be represented on a surface? The answer lies in quantum entanglement and the way information is fundamentally stored in the universe. In quantum mechanics, information isn't just about what's where. It's about correlations between particles about which states are entangled, with which about the relationships that connect seemingly separate parts of a system. And these correlations, it turns out, can be mapped onto a boundary. The information content of any region of space is proportional to the area of its boundary, not its volume. This is called the holographic bound, and it applies not just to black holes, but potentially to the entire universe. Think of it like this. Imagine a sphere around a region of space. Everything happening inside that sphere, every particle, every interaction, can be described by data on the surface of the sphere. The interior is a projection, an emergent reality, constructed from information encoded on the boundary. For black holes, this means the event horizon isn't just a passive boundary. It's an active information storage device, encoding everything that has ever fallen in. When Hawking radiation is emitted, it's not random. It's correlated with the information on the horizon in incredibly subtle ways too complex to detect with current technology, but present nonetheless. This preserves quantum mechanics. The information isn't destroyed. It's transferred from the interior to the horizon, then slowly released through Hawking radiation over the evaporation timescale. The universe remembers, always. But accepting this creates a new problem, the firewall paradox. Discovered in 2012 by Ahmed Al-Mehri, Donald Merolf, Joseph Polchinski, and James Sully, it reveals a deep conflict between different principles we thought we understood. Here's the setup. Hawking radiation is entangled with the black hole's interior. This entanglement is what allows information to escape. But quantum mechanics says a particle can only be maximally entangled with one other system at a time. You can't split entanglement. You can't have a particle correlated with 2 independent things equally. Yet the firewall paradox shows that Hawking radiation particles must be entangled with both the interior of the black hole and with earlier Hawking radiation that's already escaped. Both. Simultaneously. Which is impossible. The proposed solution is radical. Maybe the event horizon isn't smooth and empty. Maybe there's a firewall there, a region of incredibly high energy that destroys anything trying to cross, burning it to fundamental particles instantly. This would break the entanglement with the interior, solving the paradox, but creating a new problem. If there's a firewall, then the equivalence principle fails. Einstein's core insight that freely falling through a gravitational field is locally indistinguishable from floating in empty space breaks down. An astronaut falling into a black hole should feel nothing special at the horizon. But if there's a firewall, they'd be incinerated instantly. This is the dilemma. Preserve quantum mechanics and you get a firewall. Preserve the equivalence principle and information is lost. Both options seem unacceptable. Both violate principles we trust deeply. For over a decade, physicists have proposed solutions. Some suggest the paradox is resolved by quantum error correction, that the information is encoded redundantly spread across the horizon in ways that avoid the entanglement conflict. Others propose that space-time itself is emergent constructed from entanglement, and the paradox reveals this deeper structure. One of the most intriguing ideas is ER equals EPR, proposed by Juan Maldacena and Leonard Susskind in 2013. ER refers to Einstein-Rosen bridges, the technical name for wormholes. EPR refers to Einstein-Podolsky-Rosen, pairs maximally entangled particles. The conjecture is that these are the same thing. Every pair of entangled particles is connected by a microscopic wormhole, a quantum bridge through space-time, too small to send information through, too unstable to traverse, but geometrically real. Entanglement isn't just a correlation, it's a connection, a thread of space-time linking particles across distance. For black holes, this means the Hawking radiation particles are connected to the black hole's interior by wormholes. The information doesn't cross the event horizon normally. It threads through space-time geometry itself, through quantum tunnels too small to see, but fundamental to how reality works. This idea is still speculative, still being tested mathematically, but it points toward a deeper truth, that space-time and quantum mechanics aren't separate, that geometry emerges from entanglement, that what we call distance separation locality. These might all be approximations useful at large scales, but breaking down at the quantum level. And this brings us back to the book. If you burn it, the information scrambles into smoke and heat. If you throw it into a black hole, the information scrambles into Hawking radiation. Both seem irreversible. Both seem to erase the past. But physics insists the information persists, encoded in correlations too complex for us to easily read, but present nonetheless. The difference is time. For the Byrne book, reconstructing the information would require tracking billions of particles, an impossible task, practically but allowed in principle. For the black hole, reconstruction requires waiting for evaporation for trillions of years, for every bit of Hawking radiation to be emitted and its correlations analyzed. We could never do this, not remotely. But the universe doesn't care about our limitations. The laws of physics don't bend to practicality. They describe what's possible, not what's easy. In 2004, when Hawking conceded the information paradox, he gave John Preskill an encyclopedia as payment for their bet. Preskill had wagered that information is preserved in black holes. Hawking admitted defeat, though he joked that he'd given Preskill an encyclopedia from which information could be easily retrieved, unlike a black hole. But the paradox isn't fully solved, not yet. We've made progress. We understand better how information might be preserved through holographic encoding, through entanglement structures, through quantum error correction. But the precise mechanism, the detailed mathematics of how a black hole transforms in falling information into outgoing Hawking radiation, without violating any principles, remains incomplete. This incompleteness is exciting. It means there's still mystery here, still questions that push the boundaries of human understanding, still room for discoveries that might reshape how we think about reality itself. Do you think the universe keeps secrets? Or does it always leave clues written in mathematics, waiting for us to ask the right questions? The information paradox teaches us something profound. That black holes aren't just astrophysical objects. They're thought experiments, laboratories where nature stress tests our theories, revealing where they break, where they need deeper foundations. And understanding black holes at this level requires understanding entanglement, not just as a property of particles, but as the fundamental fabric from which space-time itself might be woven a fabric with geometries stranger than wormholes, connections deeper than distance. Take two particles, any two. An electron and a positron perhaps born together in a high-energy collision. They fly apart, racing in opposite directions at nearly the speed of light. One travels toward Alpha Centauri, the other toward a distant galaxy billions of light years away. The distance between them grows impossibly vast. Light from one could never reach the other within the lifetime of the universe. And yet, they remain connected. Measure one, and you instantly know something about the other. Change the spin of one and the other responds not through any signal, not through any force, but through something deeper, something Einstein called spooky action at a distance. This is quantum entanglement, and it might be the key to understanding what black holes truly are. Entanglement was discovered mathematically in 1935 by Einstein, Podolsky, and Rosen. They presented it as a problem, a paradox that proved quantum mechanics must be incomplete. They wrote a paper now, famous, showing that if quantum mechanics was correct, then measuring one particle could instantaneously affect another particle arbitrarily far away. This seemed impossible. It violated locality, the principle that objects are only influenced by their immediate surroundings. Einstein hoped this would convince physicists that quantum mechanics needed modification, needed hidden variables, some deeper layer of reality that would restore common sense and eliminate the apparent faster-than-light connection. But nature didn't cooperate. Experiments starting with John Bell's theorem in 1964 and continuing through Alan Aspect's groundbreaking tests in the early 1980s confirmed that entanglement is real. The correlations between entangled particles are stronger than any local hidden variable theory could explain. Quantum mechanics was right. Einstein's intuition for once was wrong. Entanglement doesn't allow faster-than-light communication. You can't use it to send messages. The measurement results on each particle are random. Only when you compare the results afterward do you see the correlation. But the correlation itself is instantaneous, independent of distance, woven into the quantum state in ways that transcend space-time separation. For decades, entanglement remained a curious feature of quantum mechanics, useful for quantum computing and cryptography, but seemingly unrelated to gravity or black holes. Quantum mechanics govern the small, general relativity governed the large, and the two rarely needed to speak. But in 2013, Juan Maldacena and Leonard Susskind proposed something radical. They suggested that entanglement and geometry are the same thing, that when two particles are entangled, they're connected by a wormhole, a microscopic tunnel through space-time far too small to traverse, far too unstable to survive for more than an instant, but geometrically real. They called this conjecture ER equals EPR. ER for Einstein-Rosen bridges the technical term for wormholes discovered by Einstein and Nathan Rosen in 1935, the same year as the EPR paper. EPR for Einstein-Podolsky-Rosen, the entanglement paradox. Two papers, both from 1935, both by Einstein, both describe a seemingly unrelated phenomena. Maldacena and Susskind claimed they were describing the same thing. That entanglement is a wormhole, that quantum correlations are geometric connections, that space-time itself emerges from the entanglement structure of quantum fields. This sounds like science fiction, but the mathematics supports it, at least in certain simplified models. In anti-de Sitter space, a universe with a negative curvature used in string theory calculations, researchers have shown that maximally entangled black holes are connected by wormholes. Two black holes, each in separate regions of space, linked by a bridge through space-time that connects their interiors. You can't travel through this bridge. It collapses too quickly. Any particle trying to cross would be crushed by the pinching geometry before reaching the other side. But the connection exists. Information on one side is correlated with information on the other, not through signals traveling across space, but through the wormhole geometry itself. This has profound implications for the information paradox. Remember Hawking radiation. Particles emitted from near the event horizon entangled with the black hole's interior. The firewall paradox said, these particles can't be entangled with both the interior and with previously emitted radiation. You can't have it both ways, but if entanglement is a wormhole, then maybe you can. The early Hawking radiation and the black hole interior aren't connected by entanglement in the usual sense. They're connected by a wormhole, and the newly emitted radiation can be entangled with the early radiation without violating the rules because the geometry makes room for both connections. This doesn't fully solve the paradox. The details are still being worked out, the mathematics tested and refined, but it points toward a resolution where quantum mechanics and general relativity aren't conflicting. They're two languages describing the same underlying reality, a reality where geometry and quantum information are inseparable. Mark van Ramsdonk, a physicist at the University of British Columbia, pushed this idea further. In 2010, he showed that in certain quantum field theories, if you remove entanglement between two regions, the space-time connecting them disappears. The geometry literally falls apart. Space-time in his models is held together by entanglement. Remove the quantum correlations and space itself ceases to exist. This suggests something astonishing, that space-time isn't fundamental, it's emergent. It arises from the entanglement structure of quantum fields, like temperature emerges from the motion of atoms. Temperature isn't a fundamental property, it's a statistical description of molecular kinetic energy. Similarly, space-time might be a statistical description of quantum entanglement. At the smallest scales at the Planck length, there might be no smooth space-time at all, just quantum fields entangled in complex patterns. And those patterns create the illusion of distance of geometry of the stage on which physics plays out. This idea, called emergent space-time, has gained traction in recent years. It offers a potential path toward quantum gravity, a way to reconcile general relativity's smooth space-time with quantum mechanics' discrete probabilistic nature. But it also raises unsettling questions. If space-time is emergent, what happens inside a black hole where the entanglement structure is maximally scrambled, maximally complex? Does space-time break down there? Is that what the singularity really is? Not a point of infinite density, but a region where the entanglement can no longer sustain geometry. Let's bring this back to something more tangible. In 2019, Google announced they had achieved quantum supremacy, performing a calculation on a quantum computer that would take classical computers thousands of years. The quantum computer used 53 qubits, 53 quantum bits, each entangled with the others in a carefully controlled state. 53 particles entangled. If ER equals EPR is correct, that means 53 particles connected by microscopic wormholes, forming a network, a quantum space-time, in miniature. The computation wasn't just processing information, it was manipulating geometry, changing the wormhole structure, exploring a tiny quantum universe. This is speculative, of course. We can't yet measure wormholes at the quantum scale. We don't have the technology, but the mathematics linking entanglement and geometry is becoming increasingly solid, increasingly predictive. One of the strongest pieces of evidence comes from holographic dualities, correspondences between gravitational theories in one space-time and quantum field theories without gravity in one fewer dimension. These dualities, first discovered by Juan Maldacena in 1997, show that certain quantum systems can be exactly equivalent to universes, with gravity, black holes, and all. In these dualities, entanglement in the quantum system corresponds to geometric connections in the gravitational universe. If you entangle regions of the quantum field, you create bridges in the emergent space-time. If you break the entanglement, the bridges disappear. The geometry is controlled by quantum correlations. Now, consider a black hole formed from the collapse of a massive star. As matter falls in, it becomes entangled with the black hole's interior. If ER equals EPR is correct, each infalling particle creates a tiny wormhole connecting it to the interior. The event horizon becomes a dense network of quantum bridges all tangled together, all connecting the outside universe to the hidden interior. And when Hawking radiation is emitted, it doesn't just carry energy away, it carries entanglement. It extends new wormholes connecting the black hole to the distant future, to the radiation that will eventually carry away all the information about what fell in. This is how information might escape, not by crossing the event horizon normally, which is impossible, but by threading through quantum wormholes, through connections in space-time itself that bypass the classical barriers. There's a beautiful symmetry here. Black holes are the most extreme gravitational objects. Entanglement is the most extreme quantum correlation. And they might be the same phenomenon viewed from different angles. Gravity creating geometry, quantum mechanics creating correlations, both describing the way distant parts of the universe remain connected despite separation. Einstein spent the last decades of his life trying to unify gravity and quantum mechanics, searching for a theory that would reconcile general relativity with the probabilistic nature of the quantum world. He never succeeded. He died in 1955, still convinced that quantum mechanics was incomplete, still troubled by entanglement, still searching for hidden variables that would restore determinism. But maybe he was closer than he knew. Maybe the two papers he co-authored in 1935, ER and EPR, were the seeds of the solution. Maybe entanglement and wormholes were always two sides of the same coin, waiting for someone decades later to notice the connection. Have you ever felt connected to someone far away, as if distance didn't quite matter, as if some invisible thread linked you despite the miles? Quantum mechanics says that at the deepest level, separation might be an illusion, a large-scale approximation that breaks down when you look closely enough. This perspective transforms how we think about black holes. They're not just objects that trap light. They're nodes in a quantum network regions where space-time's entanglement structure becomes so dense, so complex, that classical descriptions fail. The event horizon isn't a barrier. It's a boundary condition, a place where geometry transitions from the simple to the labyrinthine. And resolving the information and paradox, understanding what really happens when information falls into a black hole, requires understanding this transition, requires seeing how quantum entanglement weaves the fabric of space-time, how wormholes connect, what seems separate, how the universe maintains its memory, even in the darkest places. But wormholes and entanglement aren't the only tools physicists have imagined for understanding black holes at the quantum level. There are other approaches, other frameworks that attack the problem from different angles, each proposing its own vision of what space-time becomes when you zoom in far enough to see its quantum texture. What if space-time isn't smooth? What if you could zoom in far enough past atoms, past quarks, past even the smallest particles we know, and find that space itself has texture, graininess, structure? What if the fabric of reality, when viewed at the smallest possible scale, looks less like silk and more like woven thread? This is the question that drives two of the most ambitious projects in theoretical physics: loop quantum gravity and string theory. Two completely different approaches to the same impossible problem. How to unite Einstein's gravity with quantum mechanics. How to describe what happens at the Planck scale, where both theories must apply, but currently contradict each other. Neither has been proven. Neither can be tested with current technology. But both offer visions of what black holes might be at their deepest quantum level, and both suggest that the singularity, that point of infinite density at a black hole's center, might not exist at all. Loop quantum gravity starts with a radical idea: that space-time is not continuous. At the Planck scale, about 10 to the power of minus 35 meters space is quantized. It comes in discrete units, tiny loops of space-time woven together like chainmail. Distance, area, volume all become granular. At this scale, not infinitely divisible, but made of fundamental building blocks. Carlo Rovelli and Lee Smolin developed this approach in the late 1980s and early 1990s, building on earlier work by Abhay Ashtekar. They asked what would happen if you applied the mathematical techniques of quantum mechanics directly to general relativity, treating space-time itself as a quantum object. What emerged was a picture of space as a network, a graph, where nodes represent tiny volumes and links represent connections between them. Each link carries a quantum of area. Each node carries a quantum of volume. And the dynamics, the way this network changes over time, is governed by quantum equations that replace Einstein's classical field equations. In this framework, there is no smooth space-time at small scales. There are only these discrete elements, these atoms of geometry, combining to create the illusion of continuity at larger scales, the same way individual pixels create a smooth image on a screen. For black holes, loop quantum gravity makes a striking prediction. The collapse doesn't continue to a singularity. When the density reaches the Planck scale, about 10 to the power of 96 kilograms per cubic meter, a trillion times denser than atomic nuclei, quantum effects become dominant. The repulsive force of quantum geometry halts the collapse. Instead of a singularity, you get a Planck star, a tiny, incredibly dense core where the infalling matter bounces, creating outward pressure that opposes gravity. The star doesn't collapse to zero volume. It reaches a minimum size, a quantum limit, where space itself cannot compress further. From the outside, this bounce isn't visible immediately. Time dilation is so extreme near the event horizon that the bounce appears to take an enormous amount of time. But eventually, after the black hole has evaporated significantly through Hawking radiation, the bounce reaches the horizon. The black hole explodes, releasing the stored matter and information in a burst of high-energy particles. This is called a black hole to white hole transition. The white hole is a time-reversed black hole, an object that expels matter instead of absorbing it. In loop quantum gravity, every black hole eventually becomes a white hole, though the transition takes place over time scales far longer than the current age of the universe. This resolves the information paradox cleanly. Information isn't lost. It's stored in the Planck star, compressed into quantum geometry, then released when the transition occurs. The singularity never forms. The infinite density never happens. Quantum mechanics prevents it, but loop quantum gravity has limitations. It's difficult to extract predictions that can be tested experimentally. The Planck scale is so small, the energy is so high that building experiments to probe, it seems impossible with any foreseeable technology. The theory also struggles to incorporate matter and forces other than gravity in a natural way. It describes space-time's quantum structure beautifully, but has less to say about the particles and fields that live within that space-time. String theory takes a completely different approach. Instead of quantizing space-time directly, it starts with particles. But not particles as points. Particles as tiny one-dimensional strings vibrating loops of energy about 10 to the power of minus 35 meters long, a Planck length. Different vibration patterns produce different particles. One pattern is an electron, another is a quark, another is a photon. And one particular pattern discovered early in string theory's development corresponds to the graviton, the hypothetical quantum particle that carries gravitational force. This was revolutionary. String theory didn't set out to unify gravity with quantum mechanics. It was originally developed in the late 1960s to describe the strong nuclear force. But when physicists found the graviton vibration in the mathematics, they realized they had stumbled onto something bigger. A theory that naturally includes gravity, that requires gravity that cannot be formulated without it. By the 1980s, string theory had evolved into superstring theory, incorporating supersymmetry, a proposed symmetry between matter particles and force particles. And in the mid-1990s, a second revolution occurred. Physicists realized that the 5 different versions of string theory that had been developed were actually different perspectives on a single underlying theory, now called M theory. M theory requires 11 dimensions. Not just the 3 of space and 1 of time we experience, but 7 additional spatial dimensions curled up so small we can't perceive them. These extra dimensions aren't optional. The mathematics only remains consistent if they exist. In string theory, black holes are not singularities. They're configurations of strings and branes, higher dimensional objects that strings can attach to. A black hole is a highly excited state, a complex tangle of strings vibrating in patterns so intricate they create the macroscopic properties we observe. Mass charge, angular momentum, all emerge from the microscopic string dynamics. The event horizon in this picture is an emergent boundary, not fundamental, but arising from the collective behavior of countless strings, the way a traffic jam emerges from the collective behavior of individual cars. And the entropy of a black hole, the information it can store, is counted by the number of different string configurations that produce the same macroscopic black hole. In 1996, Andrew Strominger and Kumrun Vafa made a breakthrough. They calculated the entropy of a specific type of black hole in string theory by counting these microstates, these different string configurations. And they got exactly the Bekenstein-Hawking entropy. The formula Hawking derived from thermodynamics and general relativity matched the count from string theory's quantum description. This was the first time anyone had derived black hole entropy from a microscopic quantum theory. It suggested that string theory was on the right track, that it captured something real about quantum gravity. But string theory has its own challenges. Like loop quantum gravity, it makes few testable predictions at accessible energies. The strings are too small, the extra dimensions too tightly curled for current experiments to detect. The theory also has a landscape problem. There are something like 10 to the power of 500 different ways. The extra dimensions can be curled up, each producing a different low-energy physics, a different universe with different particle properties and force strengths. Which of these 500 universes is ours? String theory doesn't tell us. It offers a vast landscape of possibilities, but no clear principle for selecting the right one. Some physicists find this beautiful a multiverse where all possibilities are realized somewhere. Others find it troubling a theory that predicts everything and therefore predicts nothing. Despite their differences, loop quantum gravity and string theory share a common prediction. The singularity at the center of a black hole is not real. It's an artifact of classical general relativity, a sign that the theory breaks down at extreme densities. Quantum gravity, whatever its final form, replaces the singularity with something finite, something structured, something describable. This is important philosophically. Singularities represent places where physics fails, where our equations give nonsensical results, like infinite density or infinite curvature. They're embarrassing. They suggest incompleteness. But if quantum gravity eliminates them, if it shows that reality never actually reaches these extremes, then physics remains consistent all the way down. There are other approaches too. Asymptotic safety, which suggests gravity becomes weaker at very high energies, preventing singularities naturally. Causal dynamical triangulations, which build space-time from tiny simplices, geometric building blocks, and evolves them according to quantum rules. Each approach offers its own perspective, its own mathematical tools, its own predictions. None has emerged as clearly correct. We're still in an exploratory phase, still developing the mathematics, still searching for connections to experimental data that could guide us toward the right theory. Do you ever wonder if nature has a preference, if one of these approaches is fundamentally more real than the others, or if they're all approximations, different maps of the same territory useful in different contexts, but none capturing the full truth? The landscape of quantum gravity theories is rich but frustrating. We have multiple sophisticated frameworks, each internally consistent, each offering insights, but we lack the experimental evidence to choose between them. We're in the position astronomers were in before telescopes, philosophers before the scientific method, building theories based on reason and mathematics, but unable to test them against reality. Yet the quest continues. Because understanding quantum gravity isn't just about black holes. It's about the Big Bang, about the first moments of the universe when everything was compressed to quantum densities. It's about the ultimate fate of space-time, about whether the universe will end in heat death or collapse or something stranger. It's about the fundamental nature of reality itself, about what exists at the deepest possible level. And black holes offer the best laboratory we have for testing these ideas. They're the only places in the current universe where quantum gravity effects might be strong enough to detect, where space-time curvature is extreme enough to make the quantum structure visible. This is why physicists study black holes so intensely, not just as astrophysical objects interesting in their own right, but as windows into the quantum nature of space-time. Every observation of a black hole, every measurement of its properties, every detection of gravitational waves from a merger adds data to the puzzle, constrains the theories, narrows the possibilities. In recent years, some of these observations have become astonishingly precise, revealing not just that black holes exist, but how they behave when they collide, how space-time itself vibrates and settles after the most violent events in the cosmos, carrying information about the quantum fabric that underlies reality. On September 14, 2015, at 09:50:45 UTC, two black holes collided 1.3 billion light-years away. The event lasted less than a quarter of a second. In that brief moment, the two black holes, one 36 times the mass of the Sun, the other 29 spiraled into each other at half the speed of light, merged and released more energy than all the stars in the observable universe combined. Not as light, not as heat, as gravitational waves, ripples in space-time itself, spreading outward at the speed of light, carrying the signature of the collision across the cosmos. And on Earth, two L-shaped detectors, each with arms 4 kilometers long, detected the wave, a distortion in space-time, smaller than 1,000th the width of a proton, the first direct detection of gravitational waves. The first time humanity heard the universe ringing like a bell. LIGO, the Laser Interferometer Gravitational Wave Observatory. A project decades in the making, built to detect what Einstein himself thought would be impossible to observe. Einstein predicted gravitational waves in 1916, the same year Schwarzschild found the black hole solution. Accelerating masses, Einstein's equations showed, would create ripples in space-time disturbances that propagate outward like waves on a pond. But he calculated they'd be vanishingly weak. Even the most violent cosmic events would produce waves so faint that no instrument could ever hope to detect them. He published this conclusion in 1936, essentially declaring gravitational waves theoretically real but practically unobservable. For decades, most physicists agreed. Gravitational waves remained a mathematical curiosity, a prediction of general relativity that seemed destined to stay theoretical forever. But a few scientists, including Joseph Weber in the 1960s and Rainer Weiss in the 1970s, believed detection was possible with sufficiently sensitive instruments. Weiss proposed the interferometer design that eventually became LIGO. Two perpendicular arms, each several kilometers long, with mirrors at the ends. A laser beam splits, travels down, both arms, bounces off the mirrors, and recombines. If a gravitational wave passes through it, stretches space in one direction while compressing it in the perpendicular direction, the arms change length by different amounts. The recombined laser beams interfere slightly differently. And that difference, though extraordinarily tiny, can be measured. Building LIGO required solving engineering problems that bordered on the absurd, isolating the mirrors from seismic vibrations, from thermal fluctuations, from quantum noise in the laser itself, creating a vacuum in tubes 4 kilometers long, measuring distance changes 1 billion times smaller than an atom. The project cost over $1 billion and took decades to complete. On that September morning in 2015, LIGO had just finished a major upgrade called Advanced LIGO. designed to increase its sensitivity tenfold. The detectors had been online for only a few days, still in testing mode when the signal arrived. A chirp, a rising tone lasting a fifth of a second, sweeping from 35 Hz to 250 Hz. The scientists thought it was a test, an artificially injected signal to calibrate the system. It took hours to confirm the signal was real, that it had arrived from space, that they had detected an actual gravitational wave from an actual astrophysical event. The signal matched almost perfectly the predictions from numerical relativity computer simulations of black hole mergers based on Einstein's equations. Two black holes orbiting each other, gradually losing energy to gravitational waves, spiraling closer, accelerating, merging in a final violent moment, then settling into a single larger black hole that rang down like a struck bell. From the signal, scientists could extract extraordinary information. The masses of the two black holes, their spins, the distance to the event, the mass of the final black hole, and crucially the energy released as gravitational waves. 3 solar masses converted entirely into ripples in space-time in a fraction of a second. 3 times the mass of the sun. Gone. Not turned into matter, not into radiation, but into the vibration of space itself. This is why the peak power exceeded all the stars in the universe. For that brief moment, the merger was the brightest source of gravitational radiation in the cosmos. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of black hole mergers, some involving stellar mass black holes, some involving neutron stars colliding and forming black holes. Each event adds data, refines our understanding, tests general relativity and regimes of extreme space-time curvature. And remarkably, every merger detected so far matches Einstein's predictions. The waveforms, the frequencies, the decay times all align with the equations of general relativity to extraordinary precision. Black holes behave exactly as the theory predicts, even in the most violent conditions we can observe. But here's where quantum mechanics enters. The ring-down phase, the final moments after the merger, when the newly formed black hole settles into its equilibrium state, should carry information about the black hole's structure. In classical general relativity, a black hole has no structure. It's defined entirely by mass, charge, and spin. 3 numbers. Everything else is hidden behind the event horizon. But if the event horizon has quantum properties, if there's quantum structure there, it might leave subtle imprints on the ring-down signal, echoes, small deviations from the pure general relativity prediction, reflections of the gravitational waves bouncing off quantum features near the horizon. Several research groups have searched for these echoes in LIGO data. The idea is that if the event horizon isn't a perfectly smooth classical boundary, if there's a firewall or a quantum fuzzball or some other structure just outside the classical horizon, gravitational waves might partially reflect off it. These reflections would arrive at LIGO, slightly delayed, creating echo signals at regular intervals after the main ring-down. In 2016, Nyayesh Afshordi and his colleagues claimed to have found tentative evidence for echoes in the LIGO data, repeating signals about 0.1 seconds after the main merger. Other groups analyzed the same data and found no significant evidence. The signals, if real, are buried in noise right at the edge of detectability. This is where we are now. The echoes remain controversial, unconfirmed, tantalizing hints that might be real quantum gravity effects, or might be statistical fluctuations. Future detectors, more sensitive with better noise suppression, should be able to settle the question. But the very fact that we can search for quantum effects in black hole mergers is extraordinary. A decade ago, this was pure theory. Now, it's observational science. We're using gravitational waves to probe the quantum nature of black holes, to test whether the event horizon has structure, to constrain theories of quantum gravity. The waveforms themselves carry information about space-time at the smallest scales. When two black holes merge, their event horizons touch overlap, merge into a single horizon. This process involves space-time curvature at or near the Planck scale, where quantum effects should be important. Yet the observed waveforms match classical predictions almost perfectly. This tells us something profound. Either quantum gravity effects are incredibly subtle, leaving only tiny deviations from classical behavior, or space-time remains classical, even at these extreme curvatures, only becoming quantum at even smaller scales we haven't yet accessed. Some theoretical models predict that black hole mergers should violate general relativity in specific ways. For instance, if there are extra dimensions, if string theory is correct, gravitational waves might leak into those dimensions, carrying away more energy than general relativity predicts. The observed waveforms would decay faster than expected. LIGO has tested this. And so far, no deviations, no extra dimensions revealed, no violations of general relativity. The universe, at least in this regime, behaves exactly as Einstein predicted. This is both reassuring and frustrating. Reassuring because general relativity remains an extraordinarily successful theory, accurate even in the most extreme conditions we can observe. Frustrating because we still lack direct experimental evidence for quantum gravity, still can't definitively choose between competing theories. But gravitational wave astronomy is just beginning. LIGO and Virgo are being upgraded further. New detectors are being built. CAGRA in Japan, LIGO India, the space-based detector, LISA scheduled to launch in the 2030s, will detect lower-frequency gravitational waves from supermassive black hole mergers events, even more energetic than the stellar mass mergers LIGO observes. LISA will be able to track supermassive black holes as they spiral together over months or years, measuring their orbits with incredible precision. These measurements could reveal tiny deviations from general relativity signatures of quantum gravity effects that accumulate over the long spiral. And there's another possibility: primordial black holes. If the early universe had density fluctuations, large enough regions might have collapsed directly into black holes shortly after the Big Bang. These primordial black holes would be much smaller than stellar mass. Black holes potentially ranging from microscopic to thousands of solar masses. If they exist, and if they merge, their gravitational wave signals would be distinct from stellar mass mergers. They might reveal details about the early universe, about inflation, about the conditions when space-time itself was in a quantum state. LIGO hasn't detected primordial black holes yet, but the search continues. Each new detection, each new waveform adds to the catalog, constrains models, narrows the possibilities. There's something deeply moving about gravitational wave astronomy. We're no longer just looking at the universe. We're listening to it, hearing the vibrations of space-time itself, the echoes of collisions that happened billions of years ago, the dying songs of black holes as they merge and settle. Each waveform is unique. Each carries a story. Two black holes that formed from massive stars lived isolated for billions of years, then somehow found each other spiraled together and merged in a fraction of a second. The violence concentrated into that brief moment, the silence afterward. Do you think the universe knows we're listening? That it notices when a species finally builds instruments sensitive enough to hear space-time ring? Gravitational waves have opened a new window on the cosmos, and through that window, we're glimpsing the quantum nature of black holes, searching for echoes that would reveal structure at the event horizon, testing whether reality remains smooth at the smallest scales or becomes textured, granular, strange. These observations, combined with the theoretical frameworks we've explored, are converging toward a deeper understanding of what black holes are, what they tell us about the universe, about the nature of space and time and information itself. And as we approach the end of this journey, there's one more thing to consider, one final perspective on all we've explored, a reflection on why these questions matter. and what they reveal about the human desire to understand the darkest corners of existence. We've traveled far tonight, from the death of stars to the birth of darkness, from event horizons that trap light to the quantum whispers that let it escape, from paradoxes that break physics to theories that try to mend it, from the mathematics of Einstein to the observations of LIGO, from the very large to the impossibly small. And here we are at the end of the journey with black holes still mysterious, still beautiful, still holding secrets we haven't fully unraveled. There's something humbling about that. We've built telescopes that can see across billions of light years. We've created detectors that can measure distortions smaller than an atom. We've developed mathematical frameworks so sophisticated they require years of study to understand. And yet black holes remain partially opaque to us, their deepest nature, still hidden, still waiting for the right question, the right experiment, the right insight. But maybe that's how it should be. Maybe the universe is meant to have frontiers, places where our knowledge runs out and wonder takes over, places that remind us how much we still have to learn. Black holes do that. They sit at the intersection of everything we know and everything we don't. They connect gravity and quantum mechanics, space-time and information, the classical and the quantum, the deterministic and the probabilistic. They're laboratories where nature tests its own rules, pushing them to extremes we could never recreate artificially. And in studying them, we've learned something profound about reality itself, that it's not made of separate pieces that happen to interact. It's woven together. Entanglement connects distant particles. Wormholes might link separated regions. Space-time might emerge from quantum correlations. Everything touches everything even when it seems separate. This holistic view, this interconnectedness, is perhaps the deepest lesson black holes teach us. They show us that the universe is not a collection of isolated objects floating in empty space. It's a unified whole, a single quantum state, evolving according to laws that don't draw sharp boundaries between here and there, now and then matter and space. The information paradox at its heart is about this unity. Can information be lost? Can the past be erased? Or does the universe maintain perfect memory, keeping track of every quantum state, every interaction, every moment of history encoded somehow in the present? Physics says the universe remembers. That information is conserved, that even black holes, the darkest objects in existence, cannot erase what has been. They can only transform it, scramble it, hide it in correlations too subtle to easily decode. And there's something deeply comforting about that. The idea that nothing is truly lost, that every moment matters, that the past leaves traces, permanent imprints on the quantum state of the cosmos. We see this in small ways every day. The light from distant stars carries information about their composition, their age, their motion. Fossils preserve information about ancient life. Tree rings encode climate data from centuries past. The universe is a vast recording device, storing information in the countless forms. Black holes are just the extreme case, the place where this storage becomes most concentrated, most complex, most difficult to decode. But the principle remains. The universe keeps its records, always. This journey we've taken tonight through the quantum nature of black holes is really a journey through the heart of modern physics, through the unresolved tensions between our best theories, through the creative solutions physicists have proposed, through the experimental tests that are beginning to constrain the possibilities. We've seen how Chandrasekhar calculated the mass limit for stellar cores at 19 years old, on a ship from India using nothing but mathematics and insight. How Schwarzschild solved Einstein's equations in the trenches of World War I, finding black holes in the mathematics before anyone believed they existed in reality. How Hawking combined quantum field theory with general relativity and discovered that black holes glow, that they evaporate, that they connect thermodynamics with gravity in ways no one expected. We've explored how Bekenstein argued that black holes must have entropy, how Maldacena discovered holographic dualities, how Suskind and T. Hooft proposed that space-time might be emergent from quantum entanglement, how Ravelli and Smolin built loop quantum gravity, how string theory found black hole microstates, how LIGO detected gravitational waves from merging black holes, and opened a new window on the quantum structure of space-time. Each of these discoveries, each insight, each calculation was made by someone wondering, someone who refused to accept that black holes were simple, someone who looked at the equations and said, "There's more here, something deeper, something we're missing." And that's the most important lesson. That progress in understanding comes from questioning, from pushing against the boundaries of knowledge, from being willing to propose radical ideas and test them against reality. The quantum nature of black holes is still being discovered. The story isn't finished. New observations are coming. New theoretical insights are being developed. New connections between seemingly unrelated ideas are being found. In the coming decades, we'll have more sensitive gravitational wave detectors, better telescopes capable of imaging black hole event horizons in greater detail, quantum computers that can simulate complex entanglement patterns, perhaps even tabletop experiments that probe quantum gravity effects in controlled settings. Each will add a piece to the puzzle. Each will constrain the theories, support some ideas, rule out, others suggest new directions. Science progresses slowly, carefully, but it progresses. We understand more about black holes today than we did 10 years ago. We'll understand more in 10 years than we do today. And eventually, maybe in our lifetimes, maybe in the lifetimes of those who come after us, someone will solve the information paradox completely. Someone will show exactly how information escapes black holes, how entropy is preserved, how quantum mechanics and general relativity reconcile at the event horizon. Someone will derive black hole thermodynamics from first principles in a theory of quantum gravity that makes testable predictions. When that happens, it will be one of the great intellectual achievements of human history, comparable to Newton's laws of motion, Maxwell's equations of electromagnetism, Einstein's relativity, the development of quantum mechanics, a fundamental reorganization of how we understand reality. But even if that day never comes, even if black holes keep some secrets forever, the journey is worth taking. Because in trying to understand them, we learn about ourselves, about our capacity for wonder, about our ability to ask questions that seem impossible and slowly, patiently work toward answers. Black holes remind us that the universe is stranger than we imagine. That reality at its deepest level doesn't conform to our everyday intuitions about how things should work. That nature is creative, playful, surprising, full of connections and symmetries and paradoxes that challenge us to think more clearly, more carefully, more beautifully. And they remind us that we're part of this universe, made of atoms forged in stars governed by the same quantum laws, connected through entanglement and gravity, and the flow of information across space-time. We're not observers standing outside reality looking in. We're participants, pieces of the cosmos, trying to understand itself. When you look up at the night sky, when you see the stars scattered across the darkness, know that among them, invisible but present, are black holes, stellar remnants spinning silently, supermassive giants anchoring galaxies, maybe even primordial black holes left over from the Big Bang. Each one a question, each one a mystery, each one a laboratory where physics pushes itself to the limit. And know that people are watching them, measuring them, calculating, wondering, building theories and testing them, slowly assembling the pieces of a puzzle that might not have a final solution, but is beautiful precisely because of its difficulty. Have you ever wondered what it would be like to fall into a black hole? To cross that event horizon to see the stars compress above you, to watch the universe age and fast forward as time dilation takes hold. It's a journey no one will ever take and return to tell about. But in a sense, we're all on that journey, falling forward in time, unable to go back, watching the universe unfold one moment after another toward endings we can't fully predict. Black holes are just the cosmic version of what we all experience. the irreversibility of time, the loss of access to the past, the compression of possibilities into a single realized future. They're us, in a way, finite beings in an evolving universe trying to make sense of our trajectory through space-time. And maybe that's why we find them so compelling. Not just because they're scientifically interesting, not just because they test our theories, but because they reflect something fundamental about existence itself. The interplay of light and darkness, the tension between knowing and mystery, the beautiful, terrifying fact that some things once crossed cannot be uncrossed. Tonight we've drifted through the quantum nature of black holes, through Hawking radiation and information paradoxes, through entanglement and emergent space-time, through string theory and loop quantum gravity, through gravitational waves carrying echoes of quantum structure. We've touched on ideas that took centuries to develop, that required the combined efforts of thousands of brilliant minds, that represent the cutting edge of human understanding. And yet, the black holes themselves remain silent, patient, keeping their secrets, glowing faintly with Hawking radiation over timescales longer than the universe has existed, waiting for us to ask the right questions, waiting for nature to reveal the next clue. There's comfort in that patience. The universe doesn't rush. It doesn't demand that we understand everything immediately. It allows us to approach slowly, carefully, making mistakes, correcting them, building understanding piece by piece, generation by generation. And in that slow approach, in that patient accumulation of knowledge, there's beauty. The beauty of minds working together across time and space, building on each other's insights, creating a shared understanding that transcends any individual perspective. This is science at its best, not a collection of facts to memorize, but a living conversation with nature. A dialogue where we propose ideas, nature responds through experiments and observations, and we refine our understanding in an endless cycle of question and answer theory and test mystery and insight. Black holes are one of the deepest chapters in that conversation. They ask us to reconsider everything we thought we knew about space-time, matter information, and reality itself. They challenge us to unify theories that seem incompatible, to find connections, where none appear obvious, to trust mathematics, even when it leads to conclusions that seem absurd. And in rising to that challenge, we discover not just facts about black holes, but truths about how to think clearly, how to collaborate across disciplines, how to persist in the face of difficulty, how to remain humble before mysteries we haven't yet solved. These are lessons that extend beyond physics, lessons about approaching any complex problem with patience, creativity, and intellectual honesty, about respecting what we don't know as much as what we do, about finding beauty in questions as much as answers. So, as we close this quiet journey through the quantum shadows, remember this: black holes are not endings, they're beginnings. Beginnings of new physics, beginnings of new understanding, beginnings of questions we haven't yet learned to ask. The universe is still dreaming, still unfolding, still revealing itself in layers each deeper and stranger than the last. And we're here, conscious beings made of stardust, capable of wondering about our origins and our place in the cosmos, capable of building instruments to detect gravitational waves, capable of developing mathematics to describe quantum entanglement and emergent space-time. That's extraordinary. That's worth celebrating. That's worth staying curious about, worth staying awake just a little longer to explore. Thank you for drifting with me through these quantum mysteries. Thank you for your curiosity, your patience, your willingness to explore ideas that stretch the imagination. Thank you for being here in this moment, wondering about black holes and space-time and the deepest nature of reality. The universe has more stories to tell, more mysteries waiting in the darkness, more connections between the quantum and the cosmic, the mathematical and the physical, the known and the unknown. And we'll explore them together, one quiet night at a time, one question at a time, one discovery at a time. Until then, rest in the knowledge that the cosmos is vast and strange and beautiful, that black holes, for all their darkness, shine with quantum light. That information is never lost. That entanglement connects what seems separate. That space-time itself might be woven from quantum threads too subtle to see, but fundamental to everything that exists. Sleep well, dream gently, and know that somewhere out in the darkness between stars, black holes are spinning, glowing, evaporating, keeping their quantum secrets, waiting for the next generation of physicists to ask better questions, build better theories, make better observations. The journey continues, the mystery deepens, the universe keeps dreaming. Good night.